And your file name must be in this format. Group number underscore your processor's name. Okay. PDF. Just one. Okay. One team member does this job. Okay. If everyone in your team, submitted, it's going to be overwhelming, like a lot. That's not cool. Okay. 25%. Okay. Try your best. You still have time. And what else? Okay. This is, for example, this. Okay. Google Classroom. Okay. Through our Google Classroom. What else? Quiz number 3. Start allow 2 p.m. Okay. You may have this question. Why? Why 2 p.m.? Because your scheduling, okay, gonna come to give users like a evaluation, okay, because they need your feedback. So that's why I need to do it, finish quiz 3 before that. Okay, what is this about for our today's lecture? Multi-cores, multi-processors. Sounds so familiar, right? Okay, let's see what it is, what they are. Okay, lecture 14. This is the outline. You need to see the big picture first, because you learn a lot, right? From lecture 1 to lecture 13. You need to wrap it up and see what's going on and what's next. Okay, multiple processor organization. This is what we are going to talk about. And the big picture. Okay, you will understand what these bullets are later. Don't worry. The big picture. Single cycle, multi-cycle, pipeline, super pipeline, VLIW, super scalar. Hello, you're right. Still remember all these guys? Single cycle, multi-cycle, pipeline, super pipeline. Because quiz 3 is about this, okay, these topics. So it kind of giving you a review before final exam. Good for you, this quiz number 3. Okay, here you review. Okay, look like, let's find somebody. Find somebody to tell me about these computer architectures. Single cycle. What does it mean, single cycle? Let's say an instruction set architecture has a bunch of instructions. Each of those instructions takes one single clock cycle. Okay? Multi-cycle, more than one clock cycle. Each instruction in this architecture, okay, belongs to this architecture, take multiple clock cycles. That's why they name it like that. Okay? Pipeline, super pipeline, multiple instructions can be executed in parallel in an overlapping fashion, right? Stage 1, 2, 3, 4, 5, overlapping in parallel. Yeah, Good. Super pipeline increasing the clock rate. Okay. Basically, super pipeline is quite similar to pipeline computers, unless they increase the clock rate, okay, to make it faster. And as a consequence, they also, we're gonna have like multiple stages according to the increasing, the increased clock rate. Okay, VLIW and superscalar. Okay, multi-issue. Multi-issue. What does it mean, multi-issue? And for somebody. Yes. Multi-issue. What is? These two computers, they share one concept called multi-issue or multiple issue. What does it mean, multiple issue? Multiple instructions executed at once. Good. Very good. Okay. So how these two guys are different? Yeah, of course, they use the multi-issue concept. Okay. Compiler, very good. This one, right? Okay. This computer use the compiler to, reorder instructions to what? For what? Why they need to do that? Reordering. Why? Stalls, data dependency. Yes, hazards. Okay, to avoid hazards. Good. Okay, superscalar. It use hardware to do that, reordering to avoid hazards. Okay, so all these guys are uniprocessors. What does it mean? Just one CPU. Okay, just one CPU. Uniprocessors. And pipeline, super pipeline, we are superscalar. They use this instruction level parallelism. Okay, means multiple instructions can be executed in parallel. Okay, that's its meaning. Okay, now you remember, hopefully. So how about all today's topic? Unit processor? Is it enough? Or there's some more processor types? Yes. Basically, when you as a programmer write code, you write instruction, you have instruction instruction 1, instruction 2, and so on, right? In a sequential order, right? 1, 2, 3, 4, 5, 6. These instructions are stored in program memory or ROM. traditionally, okay, all programmers do coding like this. So, okay, skip it. You guys still remember this, right? Instruction set, instruction decode, execute, right? Memory, and write back. I encourage you guys to remember all this. Okay, just 5 stages, right? What is IF, ID? What are these? Okay, IF, ID, EX, mem, write back. Okay, give you a quick review. Instruction fresh and instruction. Or more, or multiple instructions if it's a multi-issue processor. Okay, basically fresh instructions. Instruction decode the fresh instructions and gets the required operands, maybe 1 operand, 2 operands, 3. Okay, execute. Yeah, the ALU execute the instruction. Memory, if this instruction also needs to access memory, read or write, yes, it needs this stage, the mem stage. Write back is the last stage to write the result, the obtained result to a register. Okay, write back. So when we need to deal with a register, this state and this state, okay? I just give you a clue about quiz 3, okay? When an instruction includes a register, the register must be decoded in this stage, right? And if the result must be stored, must be written back, it's going to be done in this stage, okay? Write the result into a register. So most computer programming languages, any computer programming languages requires a programmer to write code, that code like a sequential program. Okay. 1, 2, 3, 4, 5. The order of the instructions, all the instructions. And this is a review of what pipelining is. I think you guys already remember this, okay? But what I need to point out is, with the focus is this guy, okay? Superscalar. Superscalar is a form of pipelining. Okay, superscalar is here. They use this concept, instruction level parallelism. Yeah. So I just told you guys there's writing code in order, instruction 1, 2, 3, and 4, 5. Yes, the programmer sees that. But a superscalar computer, gonna reorder your program. So they're gonna be executed in different orders, okay, to avoid hazards. Okay, this is a very quick review of what you have learned, and it's very important for our today's topic, okay. The execution time, remember this? Quiz number 1 and 1 problem in the midterm exam. Remember? When I ask you to compute the execution time, you have to think about this formula. Okay. CPI times I is the number of instructions, right? And what should be below this, the line? The clock rate, okay? You guys are familiar with this formula. CPI is number of instructions and clock rate. Okay. Throughput, you have learned this already. Throughput in this context mean the number of instructions can be executed in 1 second. Okay. And it can be expressed like this, IPC. What is IPC? Okay. Times the clock rate. What, I have this question. Okay. What are the IPC and clock rate? I remember I already told you. Remember this? CPI, clock cycle per instruction. IPC, the inverse. Okay, instructions per clock cycle. So if you remember the CPI, you could remember the IPC. Okay, and for the ideal pipeline processors, the CPI is 1. The IPC is also 1. Okay, remember this. I mark, okay, these two bullets. Okay, so what are IPC? It's a very simple question, okay, and you will see this question for sure in your future. Okay, okay, like it for you. Instructions per clock cycle, and the clock rate clock cycle, right? The number of clock cycle per second. Is it too hard to remember this, and this? So, believe me, you need to remember both of them, okay? These two expressions. So what is about, why I need to point out? When we need to improve the computer performance, according to this expression, how can we improve the throughput? The computer throughput. We have this, we have this. Oh, I have already, okay. Increasing the clock frequency, okay? Increasing the IPC. It's quite straightforward, right? You want to get a higher throughput, you increase one of them, or maybe both, okay? IPC or clock rate. But remember, for the ideal pipeline processor, the maximum we can obtain for the IPC is just 1, right? Just 1. So what we can do is to increase the clock rate. So let's see what else. I have two notes here. Okay, relying on increasing clock rate. What happened if we keep increasing clock rate? Here we go. You believe it? Yes, it's true. Okay, why? Have you ever seen your main board? You have a big heatsink with a big fan on it. What are they for? Cooling your CPU down, right? If you keep increasing, implement new processor, you use a higher clock frequency, there's a, not so good. The upper bound, super hot, your CPU. Okay, so I already told you guys about the IPC, the ideal IPC is 1. In case you don't remember, okay, I have a question in lecture 13. Is it possible to make a pipeline CPI or a pipeline IPC? Okay, CPI less than 1, we prefer a CPI less than 1, right? A CPI that's less than 1. Or IPC is greater than 1 because it's the inverse. And we have already learned how to get this, right? Superscalar multi-issue, VLIW, super pipeline, okay? But there's a consequence. There's some problems. We use those processors, super pipeline, superscalar, VLIW. There's an upper bound, okay? Pipeline hazards. So what I need to summarize is increasing this guy or both, you have to face two truths, okay? Power consumption and pipeline hazards. So what else we can do in order to increase the computer throughput? Okay. By the mid of late 90s, instruction level parallelism approaches. When we talk about ILP, instruction level parallelism, you have to think about pipeline, super pipeline, VLIW, superscalar processor. Okay, remember that. This guy, ILP. Keep this, okay, in your mind. So we cannot use all those processors, improving them, because there's a point of diminishing returns. I'll show you this. One is the power consumption. Okay. Heat, okay, super hot. You see that, focus on this too, okay. Frequency, this line, yeah, this. If we increase a clock rate at some point, here, allow here, they found that it's not so good to keep increasing clock rate because power consumption gonna go high. What they file is to develop multi-cores. Okay, here multi-core. As you can see, the line is going flat. Yeah, from the I think it's around 2003, and they focus on multi-core processors instead. Okay, from this year. And you can see the increasing rate. Yes. Flat rising. You see that? So you need to understand some terms, so you would not get confused. Microprocessor. We talk about a microprocessor. You need to think about a computer chip. Okay, a computer chip. When we talk about a processor, you need to think about a CPU. Okay? CPU, processor, or core, the same thing. Okay, it's just an integrated circuit, not a chip. An integrated circuit consists of a lot of transistors. Okay, a microprocessor may have one CPU, okay, or multiple CPUs. In our previous lectures, we talk about just one single CPU. So a microprocessor has just one CPU or one processor or one core. Okay, the same thing. So don't get confused about these two terms. Processor, microprocessor. Okay, it's a chip. A microchip. And this lecture is about multi-cores. Okay, our topic, multi-core, multi-processor. So one microprocessor has more than one core, more than one CPU, or more than one processor. Where is it? Okay, for short, a multi-core or multi-core microprocessor. Okay. I told you guys about the lighting code in a sequential order, 1, 2, 3, 4. Once you need to utilize your multi-core microprocessor efficiently, you have to change your coding style. Okay, you don't do like that. You need to do something different. Okay, with the help of the operating system. Okay, we'll tell you more about these stuff shortly. Don't worry. In the past, programmer could rely on new computers, new processors. Every 18 months. You remember what that it means, 18 months? More raw. Okay. More floor. Lecture 1, I think. Without having to change a line of code, you don't need to change your coding style. But today, because it's a popular, we have modern processors. Almost all of them are multi-cores, multiple processor in a single chip, on a single chip. Okay, so you need to change your coding style to take full advantages of the multiple processors or multi-core. How? I will tell you later. Okay, don't worry. First of all, you need to understand Finn's taxonomy. He's a guy, okay, a popular guy, a famous guy. Taxonomy. We have 4 new terms. 1, 2, 3, 4. Don't be scared. Don't be scared. You will understand all of them very easily. Once you take a look at this, okay? You can get back and read them later. I want to tell you about this picture. Okay. Data stream. Instruction stream. What are they? Okay. Do it one by one. You guys are familiar with this one. Single instruction, single data stream. Or you need processors, one single CPU. Okay. So one instruction takes a set of data to compute. Like, I give you one example. 1 plus 2 is equal to 3. Okay, 1 plus 2 equal to 3, or maybe 2 divided by 1 equals to 2. Okay, one instruction, one set of data. That's all. Okay, okay, and this guy is not available, so we'll not talk about it. But it's good for you to understand what it is. Multiple instruction, single set of data. Nobody implemented yet. Okay, it's not available. Single instruction, multiple data streams. Okay, a vector processor. We are now in the AI age, right? Everything is AI, allow us. So, vector processors are now using a lot, and the prices are rising. Okay, these types of processors. Let's see what it is. For example, you have learned it from high school, right? Okay, let's see. Okay, this one maybe it's a real number. Okay. Any numbers, it's just an example. Don't worry. And you compare the computer, the a vector processor compute this. The result is in form of vectors, right? 11, 5, 14.4. This is how vector processor or SIMD processor compute. It's just two sets of data, okay? But one single instruction, right? Single instruction, this term, single instruction is just an addition. But 2 sets of data, 1, 2. Okay. I should remove this. I want you guys to get confused because we're talking about just one single instruction. Okay. One single instruction, that instruction is the addition. Okay. And one set of data, which is 1 and 2. 2 sets, 1 set of data. Okay. How about this guy? Multiple instructions, multiple data stream. Okay, more than one instruction, right? And more than one set of data for this guy. And this is what we are talking about in this lecture, multi-processor or multi-cores. Okay. we have more than one CPU. Let's say core, zero, core 1. Okay, let's say we have this processor has 3 cores. Okay, core 0, 1, oops, sorry, 2. And this is core compute 1 plus 2. Maybe this one. Okay. Maybe it doesn't have to be just additions. Let's say minus or times, okay, times. Okay. Can be any types of instructions. Okay, addition, subtractions, multiplication, division, whatever. Okay. You see, different cores compute different instructions and different sets of data, right? That's why we have multiple instruction, multiple data stream here. Okay, so if you understand this diagram, you will be able to understand all these bullets. Okay, don't worry. I have a note here. A multiprocessor. Okay, from now I think I better use just one term, multiprocessor, so you not get confused. A multiprocessor is a computer. It's a computer, of course, with at least 2 processors. Yes. If it has just one processor, it's not a multiprocessor. It's a uniprocessor. Okay, this is a fact. Okay, at least 2 processors. And one more, multiple processor. A multiprocessor may be separate computer chips, or maybe one chip with multiple cores. In the past, when they build a computer system, they use multiple processors, okay, multiple microprocessors on a single board, on one single motherboard. Okay, like fire a spread to. Let's say this is a main board, a motherboard. Okay, and this main board supports multiple CPUs in the form of microprocessors. Okay, multiple computer chips. Let's say 4. Okay, 4. You just plug these 4 microprocessor on the motherboard. Okay, and today, okay, let's say main board. And today they have this one single chip. Okay, see a computer chip. Inside, integrated circuits. Okay, for 4 CPUs inside on one single chip. Okay. A single microprocessor. It's a chip, a computer chip with 4 cores inside. Okay. Okay, hopefully you understand this. Mhm. Four cores. For microprocessors. Mhm. Okay, and today we're gonna focus on MIMD. Okay, MIMD, because you have already learned this, and this one gonna be in lecture 15. Okay, and this guy is not available, so we don't need to talk about it. But it's good for you to know what it is. Okay. Oh my goodness, we're gonna start quiz 3 uh, at 2 p.m. Okay, let me finish this. So um, let's see how many slides left. Okay, I will finish. I think get slide 21, and we stop. We, 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 we stop for a while, okay, not completely stop. Okay, let's see what it is. From now, okay, we talk about MIMD. Mhm. Oh, sorry. The first one is SISD. You, CU, the control unit, okay, one of the 5 basic components, remember? Control unit. PU or ALU, processing unit, or ALU. MU, the memory unit, okay, one of the 5 basic components, remember? Okay, so it's all you guys have learned already. So next, control unit, just one control unit. But we have multiple ALUs. You see, 1, 2, 3, 4, 5, and so on. With local memory, 1, 2, 3, and so on. Mhm. This is just one form of MIMD. Oh, sorry, SIMD. Single instruction, multiple data stream. Okay. Now MIMD for sure. And you can see this. Core, right? You combine these two units. We call, if there are 3, we say 3 cores. A core consists of a control unit and 1 processing unit or 1 ALU. Okay? And all of them share, for this structure, okay, share memory, the same memory unit. You can see that. Okay? Multiple cores share the same memory. Mm-hmm. This structure, core, okay, core again. DS is data stream. Okay, you see that data stream. They also share memory, but they have oh sorry. They are connected together to an interconnection network. Mhm. This one is supposed to be bigger than this system. Okay, you can see that uh, there's a network here. Okay, I think I need to speed up. 21. I will talk more about this guy later, okay? Because I remember now, I have some examples after this, okay? Okay, so let's talk about operating systems. What is an operating system? We all are familiar with Windows, Linux, probably Android, yes. What else? Mac OS, iOS, a lot more, many more. Okay. So what is an operating system? What is it for? Number one. Okay, let you see. Take a look at this picture. First question, what is an operating system? This is the operating system. Okay, here. Application software. Operating system is the middle guy, right, between applications software and the hardware, which is a computer. A computer. Okay. Application programs like Microsoft Excel, games, web browser, whatever the user use, okay. So what the user sees would be this one, okay, application software. Okay, when you open your programs, a program, you can see it on your monitor. Mm-hmm. But the operating system, I think it's hard to say, right? If you're not an expert, you don't know how to access the operating system. Okay. Below is the computer. The 5 basic components are in this. Okay, this block. You see that? What is it? Execution hardware. CPU. Okay, CPU is here. System interconnection. Probably system bus. Okay. Memory, right? Input, output, Memory. Five basic components. Control part. Control unit. Okay. Data path. Memory. Input. Output. Right? Yeah. So you can find them. You know? Okay, the next question. What is an operating system for? First, for convenience. Second, efficiency. Think about you buy a computer and it doesn't have any operating systems. It would be painful, really difficult to use it. Let me share my story. My first computer, really long time ago, a few decades ago. Okay, okay. No operating system. When I turn it on, what I saw just a black screen, nothing, and a command prompt. When I need to use it, really hard. It was very difficult. But today, when you turn your computer on, wow, beautiful screen. You can click whatever you want with the operating system, Windows, or whatever operating system you're using. Mm-hmm. So, for convenience, right? Efficiency. Your computer provides many resources. What kind of resources? Memory, okay? Inputs, outputs. Many inputs and outputs, okay? Keyboard, a mouse, a camera, a monitor, many inputs and outputs. If your computer doesn't have any inputs and outputs, what can happen? Your computer would be useless, right? You cannot do anything with your computer. I would say that. So these are precious resources that your operating system need to take care of. Okay, if you have to do it on your own manually, really hard. Okay. Okay. So this is a summary. Your operating system typically provides these services. Execute your programs, your software applications, yes. Take care of inputs, outputs devices, yes. Files, any formats, right? System access. You gotta remember, when we talk about the ARM, you have we talk about the 7 privilege modes. It is some protect resources, okay, allow for the operating system to handle, not the user. Okay, the user cannot do anything with that because to prevent any malicious guys to ruin the whole system. Okay, so the operating system itself is a resource manager because the processor is also a resource. Mm-hmm. Think about when you run multiple applications on your computer. Run all of them at the same time. You watch a movie, you listen to music, you are typing your report, working on your report, whatever, multitask. The operating system will take care of all this. Okay. Okay. Process and thread. I think the last slide, okay, before we start the quiz. Let's say we are learning, you are learning 3 programs. One program is regarded as a process. One process for one program. You watching a movie, okay, one process. You using an Excel, one process. Okay. One process consists of multiple threads. Threads is basically a block of instructions. For example, okay, I have an example here. You are using a word processor. Okay, a word processor is one process, right? And this process consists of many threads. Handling the keyboard, okay, your keyboard, spell checking, printing, whatever the word processor can do for you. Okay, you can see that there are so many threads. If you're running many programs, many processes, okay, so the operating system will control all the processes, all the threads for you, running all of them together. Okay, we stop here for a while. Give me one moment. We're going to start exactly at 2 p.m. Let me finish my explanation. Okay, thank you. Open book, calculator, allow, no problem. Any smart devices, go ahead. 40 minutes, okay? It might look complicated at your first glance, but believe me, you're going to be fine. Okay. Okay, go ahead. 40 minutes. So now it's 2 p.m. We're gonna finish around 2:45, right? 2:45. The first problem, true or false, okay?